Here is a fact that sounds made up. Building a jet engine is harder than building a rocket. Not slightly harder, significantly harder. A rocket engine burns for maybe 8 minutes. A jet engine has to burn, spin, and survive at temperatures hotter than lava for 20,000 hours straight, carrying 200 lives at 35,000 feet. And if anything fails up there, there is no pulling over. There is no second chance. For 50 years, only a small club of Western nations had truly cracked this problem. The United States, France, the United Kingdom. They didn't just build the best engines in the world. They built a system so locked up, so layered with patents, export laws, and decades of proprietary knowledge that breaking in wasn't just difficult, it was considered basically impossible. Engineers who had spent careers in the industry would tell you plainly, the gap is too big, the head start is too large, nobody is catching up in our lifetime. Then China quietly decided to prove them wrong. What happened next didn't come with a dramatic announcement or a splashy reveal. There were no fireworks, no press conferences with world leaders. Just a steady, state-funded program grinding away in the background, decade after decade, while the rest of the world assumed nothing significant was happening. And then, the test results started coming in. And the numbers were not what anyone on the outside expected to see. China didn't just build an engine. They started dismantling a dependency that was engineered specifically to last forever. And the speed at which they did it is what has aerospace engineers in the West genuinely paying attention right now. If that sounds like the kind of story you want to understand properly, hit like and subscribe before we go further. This one goes deep, and you won't want to miss what's coming next. Because to understand the full weight of what China actually pulled off, you first need to understand the crisis that cracked the door open for them in the first place. The shortage that changed everything. In 2022, the world opened back up. Airports went from ghost towns to gridlock almost overnight. Airlines that had been bleeding cash for 2 straight years suddenly had passengers flooding back faster than any forecast predicted. Every carrier on the planet needed new planes, and almost nobody had them. Boeing was sitting on a backlog of over 5,600 undelivered aircraft. Read that again slowly. 5,600 planes, paid for, contracted, signed, and waiting. Airbus had its own enormous pile of delays. Carriers were being told their new planes might arrive in 2027, maybe 2028, possibly later. But the backlog alone wasn't even the worst part. Even when aircraft bodies were physically sitting on the production floor ready to go, the engines weren't showing up. Because the same supply chain collapse that hit car manufacturers and electronics companies hit aerospace too. The special metal alloys required for turbine blades, the heat-resistant ceramic coatings, the precision castings that have to be perfect every single time. None of this stuff comes off a regular factory floor. Every piece is specialty work built by a small number of suppliers worldwide. And the whole system had locked up. For a small or mid-size airline, this created a genuinely painful math problem. You needed planes to compete. Your rivals were finding workarounds and expanding their routes. Your passengers were actively booking tickets. And the two companies that had controlled commercial aviation for half a century, Boeing and Airbus, simply could not move fast enough to solve your problem. You were on a waiting list, and there was nothing you could do about it. That's when something shifted. Airlines that had never seriously entertained the idea started asking questions about a plane built in Shanghai. A plane called the C919, made by a Chinese manufacturer called Comac. And that conversation changed the entire landscape of what was possible. Now, the C919 is not a revolutionary aircraft by any technical measure. It has a shorter range than an Airbus A320neo. It burns slightly more fuel. The airframe carries a bit more weight than its Western rivals. By the standards of the aviation industry, it is a solid but unspectacular machine. But in a world where the alternative was waiting 3 years, unspectacular started looking extremely attractive. There is an old truth in business that keeps proving itself right. The best product doesn't always win. The available product does. For the first time in the history of commercial aviation, China had the available product. A door that the West had spent decades keeping tightly shut had started to open. But here is the part that matters most, and it's the part that almost nobody was talking about publicly. That door had a serious structural problem hiding right behind it, and it had everything to do with what was bolted to the wings of that plane. The leash that nobody saw. When you looked at the C919 in those early commercial years, you were looking at a Chinese aircraft powered by a Western engine, specifically the CFM LEAP 1C, built by CFM International, which is a joint venture between GE Aerospace of the United States and Safran of France, two of the most powerful aerospace companies on Earth, both Western, both operating fully under Western export law. Most people hear engine and think it's just hardware. You bolt it on, it burns fuel, the plane flies. That is not even close to how this works in the real world. When an airline buys a CFM engine, they are not buying something they fully own and control. They are buying into an entire ecosystem that never really leaves the manufacturer's hands. Think about what that looks like in day-to-day operation. Every spare part that keeps that engine running, every blade, every seal, every sensor is sourced and certified through CFM. The software controlling how the engine manages its own power, its diagnostics, its performance tuning, is managed and updated by the manufacturer. Maintenance has to happen at approved facilities, carried out by certified technicians, using proprietary tools that only CFM provides. And if you want to fly internationally on routes that matter commercially, the regulators in Europe and the United States need to remain cooperative. Without their sign-off, those routes disappear. Every single one of those touch points is a point of leverage. And here is why that leverage shifted from a business inconvenience into a genuine national concern for Beijing. The United States had already shown, clearly and publicly, that it was willing to weaponize technology access when political pressure built high enough. When tensions in the semiconductor space escalated, Washington cut companies like Huawei and SMIC off from American components with a few regulatory changes. Entire product lines died. Supply chains that took years to build collapsed in months. The message from that episode was impossible to misread. If the political temperature gets hot enough, the access gets cut. So Beijing looked at the C919 and saw the obvious and uncomfortable question: what happens if tensions over Taiwan escalate into something more serious? What happens if new sanctions hit the aerospace sector the same way they hit semiconductors? What happens if CFM is told one morning that servicing Chinese airlines is no longer permitted? The answer isn't just a business problem. Overnight, it becomes an operational catastrophe. Planes that cannot fly, airlines that cannot operate. A national aviation program that collapses not because of anything it did wrong technically, but because of a political decision made in Washington. That is not a hypothetical designed to sound dramatic. It is a documented, mapped out, strategic vulnerability. And every engineer and government official connected to the C919 program understood it completely. So here was the uncomfortable reality that sat underneath all the good news about orders and airline interest. China had an aircraft in the sky. Chinese carriers were taking deliveries. The Western press was starting to notice Comac. But the engine powering that aircraft, the single most critical system on the entire plane, still belonged to someone else. The leash was still fully attached. And that leash wasn't there by accident. Western Aerospace didn't just build great engines. They built a system of dependency so deep, so layered into global aviation infrastructure, that escaping it was supposed to be the permanent advantage. The moat that never dried up, the wall that never fell. supposed to be. Because while all of this was playing out publicly, something else was happening quietly in Chinese test facilities that would eventually make Western aerospace engineers sit up straight. The hardest thing humans have ever built. Before we get to what China actually built, you need to feel the weight of what building a jet engine really means. Because if you skip this part, the achievement doesn't land the way it should. And this is directly why what happened next shocked the people who know this industry best. A jet engine pulls air in from the front, compresses it under enormous pressure, mixes it with fuel, ignites it, and pushes it out the back at tremendous speed. When you describe it like that, it almost sounds manageable. The reality is something else entirely. Inside that engine, blades roughly the size of your hand are spinning at over 10,000 rotations per minute. The gas flowing around those blades reaches temperatures above 1,600 degrees Celsius. To give that number a reference point, you can actually feel that is hotter than the lava flowing out of an active volcano. And those blades absolutely cannot melt, cannot crack, cannot fail. Not for one flight, not for 100 flights. They have to survive that environment for 20,000 flight hours without a single critical failure. Because a failure at 35,000 feet over an ocean is not a recoverable situation. To make that possible, engineers had to invent materials that don't exist anywhere in nature. The turbine blades are grown as single crystals, meaning each blade is one unbroken metal structure with no internal boundaries where microscopic cracks could start and spread. Tiny cooling channels, some of them thinner than a single human hair, are drilled through each blade using laser equipment so that a thin film of cooler air can flow through and protect the metal from the incredible heat surrounding it. The outside of each blade is then coated in a ceramic layer measured in millionths of a meter, giving it one more line of defense. Every single one of those innovations took years of dedicated research to develop. GE and Pratt & Whitney started laying the groundwork for what their engines can do today back in the 1970s. The LEAP engine that entered commercial service in 2016 is built on 50 years of accumulated knowledge, failed experiments, engineering breakthroughs, and billions of dollars spent chasing marginal improvements. You cannot shortcut that process by studying it in a textbook. The knowledge lives in the hands and the institutions that built it. That was the wall, half a century tall, paid for in time, money, and a kind of institutional expertise that doesn't transfer easily. And for a long time, it held exactly as intended. Here is where the story of the engine that shocked the West actually begins. What China quietly built. While the C919 was flying passengers on CFM engines, while that dependency was still fully in place, a separate program was picking up serious speed inside China. The engine is called the CJ1000A, developed by a state-owned company called AECC, and it has one clear purpose: replace the LEAP 1C entirely, own the full aircraft, cut the leash for good. To be straightforward about where things stand today, this engine is not yet certified for commercial passenger service. It has not logged the extended flight hours that aviation regulators require before allowing passengers on board. Its reliability record doesn't come close to matching the LEAP 1C, which has hundreds of millions of operating hours across thousands of aircraft on every major route in the world. By any current measure, it is not ready to compete head-to-head with what GE has built over 5 decades. But that framing misses the actual story entirely. The shock is not that the engine exists. The shock is the speed at which the gap between where China started and where it needs to be is closing. And that speed is the thing that Western aerospace analysts were not prepared for. Flight testing on the CJ1000A began in earnest in 2023, mounted on a large Chinese military transport aircraft used specifically as a flying testbed. In early 2025, engineers inside AECC reported that test performance was exceeding their most optimistic internal projections. Turbine temperature performance was approaching levels that, 10 years earlier, Chinese metallurgy had no realistic engineering path to reach. Thrust figures were entering ranges that outside analysts had not expected to see for another decade. Over 6,000 hours of environmental testing had been logged, covering extreme cold temperatures, high-altitude conditions, icing scenarios, and bird strike testing that regulators require. By 2026, a modified C919 airframe had been prepared specifically for verification flights using the new domestic engine. Industry analysts tracking the program closely were pointing to 2027 or 2028 as a realistic window for receiving certification from Chinese aviation authorities. That is not a distant, abstract goal anymore. That is a near-term engineering milestone. Now here is the question that cuts through all the technical detail. Does the CJ1000A need to beat the LEAP 1C to matter? It doesn't, not even close. China doesn't need to build the best engine in the world to change the entire strategic picture. It needs to build an engine that is good enough for Chinese airlines, flying Chinese domestic and regional routes within a Chinese regulatory framework. The moment that threshold is crossed and the engine enters commercial service, even on a single domestic route between two Chinese cities, the entire leverage equation flips. China controls the parts supply. China controls the software updates. China controls the maintenance approvals. China controls what gets exported and to whom. No political conversation about sanctions or export controls ever starts with, "And by the way, your engines." That's not just engineering independence. That is geopolitical independence. And Beijing understood that distinction clearly before the first turbine blade was ever cast in a Chinese foundry. The engine that shocked the West isn't shocking because of what it can do today. It's shocking because of what it makes possible tomorrow. And to understand how China got here this fast, you need to understand something about how they think about time that is fundamentally different from how Western companies operate. The game nobody else wanted to play. When the CJ1000A program was formally approved and funded, the people running it made no assumptions about shortcuts. They looked at what GE spent 50 years building, at the billions of dollars and the generations of engineers behind the LEAP engine, and they made a simple calculation. Fine. We will start now. 20 years sounds like a long time when you say it out loud. In China's national strategic planning, it is a project timeline, not a delay, not a compromise, a plan. Western aerospace companies are built around a completely different clock. They answer to shareholders on a quarterly basis. Major technology decisions run through 18-month approval cycles. Long-term research programs that don't show returns for a decade struggle to survive budget reviews. When a technology realistically requires 50 years to develop from scratch, the corporate structure of a publicly traded Western company makes that commitment nearly impossible to sustain. The incentive system works against it at every level. China's approach to the CJ1000A bypassed that problem entirely. The program was funded at the national level, insulated from short-term financial pressures, and given explicit protection across multiple 5-year planning cycles. It survived shifts in economic conditions. It survived periods when outside observers declared it stalled or permanently behind. It kept accumulating test hours, refining materials, and solving engineering problems one at a time, year after year, regardless of what the quarterly earnings calendar said. Think about it this way. If two runners start the same race, but one of them begins 100 meters behind, the only question that determines the outcome is not who is ahead right now. The question is whether the trailing runner is faster, because if they are moving faster, the end of that race is already decided. You just have to watch enough laps go by to see it happen. China is the trailing runner in commercial aviation. The gap is still real and measurable. The LEAP 1C, has a reliability record and a commercial history that the CJ1000A cannot match today. Comac delivered only about 15 C919 aircraft in all of 2025, far short of its targets. And the 2026 goal of 28 deliveries is being called a stretch by serious analysts. International certification from European and American regulators is not on the near-term horizon. But none of those current limitations change what the trajectory looks like when you step back far enough. Every flight hour accumulated on the CJ1000A adds to a foundation of reliability data. Every engineering problem solved in testing removes one more obstacle between the program and certification. Every C919 that flies a domestic route in China adds to the ecosystem of trained mechanics, spare parts, logistics, and operational knowledge that a mature aviation program requires. China is building the market and the technology at the same time, feeding each one into the other deliberately. The West spent 50 years building a wall around commercial jet engine technology. And the shock of what China has done is not that they knocked the wall down, it's that they built a door in it. Quietly, methodically, faster than anyone watching from the outside thought was possible. The gap that was supposed to be permanent is measurably closing. And in aviation, that changes everything that comes after it. If this story hit different than you expected, the like button is right there, and it genuinely helps. Subscribe and turn on notifications so you catch the next deep dive when it drops. And I want to hear from you in the comments. Do you think international passengers outside China will ever fully trust a homegrown Chinese engine with their lives at 35,000 feet? Let me know what you think below.